Mechanisms behind time-restricted eating effects in animals versus humans. Why results diverge. The dramatic metabolic improvements observed in rodent time-restricted eating studies have fueled enthusiasm for human applications, yet human trials consistently produce more modest results that pale beside animal findings. This translational gap, far from representing scientific failure, illuminates fundamental differences between animal models and human contexts that affect how dietary timing interventions operate. Understanding these divergences proves essential for setting realistic expectations and identifying which mechanistic insights from animal research likely apply to human metabolism. The circadian biology differences begin with activity patterns. Laboratory mice are nocturnal, naturally active and feeding during dark phases. Standard housing provides 12-hour light-dark cycles, and ad libitum feeding allows constant food access. Many mice develop eating patterns extending across 15 to 18 hours, consuming food throughout their active phase and even during rest periods. This pattern, while natural given constant food availability, represents circadian misalignment, eating during biological rest phases. Time-restricted eating interventions that limit feeding to 8 to 12 hours during the active dark phase essentially restore circadian alignment, correcting a laboratory-induced dysfunction. The intervention's success partly reflects reversal of artifact rather than optimization beyond normal physiology. Humans, conversely, typically don't face equivalent baseline circadian misalignment in non-shift worker populations. Most people naturally consume food during daylight hours, aligned with their diurnal activity pattern. While eating windows may extend longer than optimal, the dramatic misalignment of rodents eating during biological rest doesn't typically occur. Time-restricted eating in humans tweaks existing patterns rather than correcting profound misalignment, explaining smaller effect magnitudes. The human intervention refines timing that's already reasonably aligned rather than restoring fundamental circadian order. The dietary context differs substantially. Animal studies employ controlled, nutritionally complete diets with fixed macronutrient ratios. Ad libitum-fed control rodents often overeat, developing obesity and metabolic dysfunction that provides substantial room for improvement. Time-restricted groups receive identical food but within limited windows, automatically reducing intake while preventing overeating. Human studies face messy dietary reality, variable food quality, composition changes across time periods, social influences, and emotional eating. These uncontrolled factors introduce variance and potentially dilute timing-specific effects through confounding dietary changes. The environmental control in animal research creates conditions impossible to replicate in human studies. Temperature, humidity, light exposure, stress, and activity levels remain constant for laboratory rodents, isolating meal timing effects from environmental perturbations. Humans inhabit complex social environments with variable schedules, stress exposures, sleep disruption, and countless factors affecting metabolism beyond meal timing. This environmental noise obscures subtle timing effects that emerge clearly in controlled animal conditions. The animal findings may accurately capture timing effects under idealized conditions that rarely exist in human contexts. Genetic homogeneity of inbred research strains versus human genetic diversity affects response consistency. Mouse studies typically employ genetically identical animals, eliminating inter-individual variation and enabling small sample sizes to detect effects. Human genetic variation creates substantial response heterogeneity, with some individuals responding robustly and others minimally or negatively. Population-averaged human effects appear modest even when subgroups show meaningful responses obscured by averaging across genetic and lifestyle diversity. The metabolic dysfunction severity in study populations matters. Rodent studies often use obesity-prone strains or diets inducing severe metabolic dysfunction, creating large treatment effect ceilings. Human time-restricted eating trials increasingly recruit metabolically healthy volunteers or those with mild dysfunction, populations with less improvement potential. When human studies specifically recruit participants with metabolic syndrome or prediabetes, effect sizes increase, approaching but rarely matching rodent magnitudes. The mechanistic insights from animal research remain valuable despite translational challenges. Circadian clock mechanisms, autophagy regulation, and metabolic pathway oscillations discovered in rodent studies likely operate similarly in humans. However, the magnitude of effects achievable through timing manipulation alone, without the dramatic circadian realignment possible in nocturnal rodents with reversed feeding patterns, appears more modest in humans. The rodent findings establish biological plausibility and mechanism, but overestimate practical human impact when interpreted without accounting for contextual differences. Future human research should acknowledge these translational limitations explicitly, setting realistic effect size expectations based on human data rather than animal projections. Conversely, animal research should explore more naturalistic scenarios, perhaps studying time restriction in rodents already exhibiting circadian-aligned feeding, to better model human contexts. The goal isn't achieving perfect animal-human concordance, but rather understanding when and why findings translate successfully and when species or contextual differences limit applicability. This nuanced perspective better serves both basic science and clinical translation.